to listen to the talk from organizers. So we will talk about the Plankton models, interaction of time delay and spatial effects. So please.
Okay, so I didn't get the memo last night about talking, so I didn't spend the night revising my slides, which is why this says 2018. But anyways, I wanted to talk about something that I think is more relevant to this audience. So newer talks that I had are more about neural systems. So this is some old work with I got it, yeah. Francis Poulin is a professor in my department who works on fluid mechanics, but he's also very interested in Plankton models. And Matt Klusterman was a PhD student we co-supervised because Francis was interested in introducing time delays in some models that he had looked at. And there is more recent work. We had a new visiting PhD student from China, Yiwen Tao, and she actually pursued this spatial. This is really just going to introduce the idea of spatial effects, which Matt just sort of touched in his PhD. And then Yiwen came for a year and did some great work, which came out last year in SciEm, but I didn't have a chance to add that. So, but anyways, so I'll give you the overview. So we'll do a little introduction on these Plankton models, the types that we're looking at, and look at equilibrium points, and then looking at the effect of. So we want to look at the effect of time delay and diffusion on what happens in the model, and then a few simulations and some conclusions at the end. Okay, so just a little intro about Plankton, and we have experts more than me, such as Shigui in the audience. We've benefited very much from your papers. So Plankton are free-floating organisms in the oceans. So we have phytoplankton, like algae, and then smaller things like little shrimp. They form the bottom of the food chain, right? So it's very important. Phytoplankton, as I said, are like green algae, cyanobacteria, and zooplankton are things like insect larvae, jellyfish, small crustacean. So the phytoplankton are kind of like the prey, and the zooplankton like the predators. And so why do we bother studying them? Well, as I mentioned, they're the bottom of the food chain, so we need to understand what happens to them because it affects everything above them. They can exhibit blooms. So this is a picture of Vancouver Island, an aerial photo, and there's Washington State down there. And the green here is actually a bloom of phytoplankton. So you can actually see these from space. So that can affect the whole ecosystem. Some blooms are toxic, right? They have toxic things in them, so they can affect the ability to go swimming or use the water. So we need to understand kind of how this can happen. And they're very important in the transfer of carbon dioxide from the atmosphere to the ocean. They form a carbon sink in the ocean. And so that's another reason to understand kind of how they affect things. And this is a few years ago that, 2012, somebody decided to do a biogeoengineering where they sort of set up phytoplankton to do a carbon sink in the ocean, which people weren't very happy about. So yeah, so this is, when we're all thinking about global warming and then how does that affect things. So just sort of our motivation here. So the model that we're going to look at is going to have 3 compartments. So I've mentioned the phytoplankton and the zooplankton, but we're also going to keep track of the nutrients. So it's a 3 trophic level model. So it's like nutrient, and these are the grazers. And then these are sort of the prey, and then these are the predators. So I've got a model here. And there's many things you can pay attention to. What we're going to be interested in this model is thinking about nutrient recycling. So after the organisms die, they get recycled by bacteria, and the nutrient goes back and then can be taken out. So we have this sort of chain of the nutrient moving around in the system, and this is for this model, the key was sort of introducing this recycling. Okay, so here's the basic model, just the starting point, and I'll just go over the pieces of it. So the phytoplankton nutrient uptake, that's sort of a standard uptake function here with F, so we'll talk about that later. Mu is the proportionality constant, sort of growth rate constant. And then we have the zooplankton grazing on the phytoplankton. So this is like a predator-prey type term, right? So we have loss in the prey and gain in the predator, and then we have nutrient recycling. So we recycle, there's always a loss, right, from the predator to the prey because of this gamma, because they can't turn everything they eat into biomass. And so that loss is recycled into the system. And then we also have death, right? And so after the organisms die, again, that biomass is recycled in the system, right, through being broken down by bacteria. So this, yeah, I think this is, oops, I'm going the wrong way. There we go. This basic model was one that Francis Poulenc had looked at before. And then what we were interested in, the nutrient recycling takes time. So the first thing we looked at, so let me say a little bit about functional responses. I'm getting ahead of myself. So we have two functional responses, right? We have the nutrient uptake by the phytoplankton, that's the F. And so typically that's taken to be Michaelis-Menten type 2 or Monod type 2, right? So it has some concavity assumptions. And then we have the zooplankton grazing on the phytoplankton, that's the H function. And that can be type, based on sort of literature, that can be type 2 or 3. And with these zooplankton and phytoplankton, well, especially zooplankton, they actually do little experiments in labs where they try and measure some of these things. So that's just illustrating the two types. So we will pay attention a little bit to this. It's quite important which one you choose here. It affects, and I think Gail mentioned this the other day, it really affects what can happen in the model. Okay, and so, yeah, so here's the ODE model. And as I mentioned, yeah, this is what I was saying the other side, that Francis Poulenc had a previous paper on this, and what he was interested in was, you know, if we really take into account that this recycling doesn't happen instantaneously, but it takes some time, how do we incorporate that into the model? So the first thing we did, which is a part of Matt's work, was incorporate a distributed delay, right? So we take all those recycling terms, we're calling all that recycling terms together, Q of P minus U. We have a distribution function eta, you know, we have a typical distributed delay function in there. So the integral represents, they call it detritus. It's the dead plankton, dead zooplankton, can be the fecal pellets, and these are in the process of being recycled. So that's kind of what that term is representing. The distribution, right? So typical thing, the eta integral is 1, and we'll pay attention to the mean delay tau, because we'll think about that. In some ways that'll come up as a parameter that we want to think about how that affects things. So examples, gamma distribution, we saw that earlier today. You can also take it, if you take it just a Dirac, then you get back to a discrete distribution. And then we also looked a bit at uniform, but I won't say that. So here's the gamma, we saw this picture already. Here we've taken a fixed mean delay of 2, and then we're varying. So I formulated it in terms of the mean delay and the parameter P, which determines essentially the sharpness of the peak, just for simplicity. So slightly different parameters than what was used in the first talk. So you can see how the different value of P affects the kind of distribution. And right, so then the first thing that Matt did, and there's a whole paper from like 2014 in Journal of Math Biology, just putting in the distribution, and I'll say a little bit about those results and how the different distributions affected it. But of course, this thing's all happening in water, right? So the next sort of step was to start thinking about what happens if these things are floating around. And the very first step to that was just thinking about diffusion. So we could put other things in, like the plankton can sort of propel themselves around. So you might want to put a different type of term. But the first thing we decided to do is just put in some diffusion, just basic. So we're going to just do one in one dimension. So, I mean, really, we're thinking about sort of a column of water and sort of in one dimension. And so you have to put the diffusion in, and if you have diffusion and delay, you have to be very careful about how you put that in. So I benefited from reading papers, I think Xiao Chiang and a few other people and Michael Lee, about writing that in properly. So what we've got here is a double integral. We have a kernel here. Here's that same Q, which represents all those terms of the stuff that's being recycled. But we have a kernel that depends, well, the way we set it up here is so it depends on space and time. So this double integral, because we want to take into effect that as you know, if you want to think about the stuff that happened what happened in the past, but in that interim, it can be moving around, right? So you need to take into account that this term has to take into account the stuff was in the past, but could have been somewhere else, let's put it that way. So we have this double integral, and so you have to think about how to choose that kernel. And there's been some nice work on that. What Matt did, which was kind of a nice way to sort of think about it, was they start with this DDE, and if we choose the gamma distribution with integer p, then we can do a reduction, right? And he sort of did this, well, if you do the linear chain reduction on the DDE, and then you add the diffusion, versus if you add the diffusion, I'm losing the thing again, add the diffusion and then do the linear chain, you should get back to the same PDE. And so that actually is one way of sort of looking at what's a good way of introducing the kernel. And there's other methods. And essentially you get down to a little PDE for the kernel with appropriate initial conditions. And so you can solve for that. Okay, and so notice that it introduces yet another diffusion constant because we have to think about the kernel representing how the stuff is moving around while it's being recycled. And there's different ways that you could think about choosing that. We'll talk at the end about how we choose that. So we now have sort of 4 diffusion constants, 3, one for the nutrient, one for the phytoplankton, one for the zooplankton, and now we have another one that's associated with the stuff that's being recycled. Okay, so then we get our whole model put together. We've got some, as I said, x and 0L. We can think of that maybe as a column of water. We have no flux boundary conditions, and we have our kernel. And so we can then start to do some analysis. Oh, and so the parameter values, again, this was taken from a previous paper of Francis and some other papers where they had looked at sort of appropriate values. So all our simulations, we use these sort of reasonable values from the literature. And as I said, either we use for the phytoplankton, it seems to be the type 1 is, or sorry, the type 2 is reasonable, but for the zooplankton, type 2 or type 3 might be good. So we'll play around a little bit with both of those. Okay. And I'm missing a ton of references. As I said, Shigui has done a ton of work on these plankton models, and also Stephen Gourley, I never say his name right, has a very good, like we've benefited a lot from those papers and sort of formulating, and especially when we got to doing the more recent work on the spatial temporal. So this model is a little different than some models. It's not a chemotype type model. It's actually a conservation model. So if you remember my little diagram at the beginning, the nutrient was moving all around, and then so the total amount of nutrient in the system is conserved. So all the terms, you know, if you add them all up, you see that the total amount of nutrient in the system, and because we're looking at this nutrient recycling, so we're keeping track of that. So within the ODE model, that's what our conservation law looks like. And so in the ODE model, of course, you can take a 3D system and reduce it to a 2D system, and we have this parameter of the total nutrient, and we'll end up using that as a bifurcation parameter in this system. But what happens if we put in our distributed delay and diffusion, right? Do we still have a conservation law? And what does it mean? So it turns out we do have a conservation law, and it looks something like this. So the total nutrient in the system is conserved, and this is sort of the integral over L of n plus p plus z. So that's like integral over our water column of our nutrient, our phytoplankton, our zooplankton. And then we get this other integral to make the conservation law work. We have this other integral that has to be in there. And of course, what this represents is that nutrient that's in the process of being recycled. So we do have a conservation law, but it's not just the total amount of organisms. It's also have to sort of take into account the things that are being recycled. Okay, so we have this, and so we can't do like a reduction or anything in this case, but we have to take that into account. So let me tell you a little bit, we'll look at spatially independent solutions, and I can say a lot about that and a little bit about their stability and bifurcations. So when we look at spatially independent equilibrium solutions, if we look, for instance, at this, we end up with 2 just because of the way the equations come out. There's just 2 equations that they have to satisfy, but the third equation comes from the conservation law. So we can solve for NP and Z in terms of these two equations that come from the differential equations and one from the conservation law. And so what kinds of equilibrium points can we have? There's basically three types. So we could have sort of, we call the trivial one, where we just have nutrient, okay? And this is in the sort of biologically reasonable position as long as the amount of nutrient in the system is positive. We can have an equilibrium point where we only have nutrient and phytoplankton, right? And that will lie in the positive orthant, so meaning p hat will be positive or non-negative, only if the total nutrient is big enough, right? So if NT is bigger than this NT1, which we can formulate in terms of the parameter systems, lambda and mu have to do with their growth rates, L has to do with the size of the system. And so it says what kind of when you sense, we expect you have to have enough nutrient there to be able to support the phytoplankton. If you don't have enough, then essentially they'll die off. And we have a coexistence where we have nutrient, phytoplankton, and zooplankton. And again, we can sort of, not really important, we can formulate what those expressions are for P and N and Z. And again, we have another threshold that we have to have enough nutrient in the system. So NT has to be bigger than NT2, which is bigger than this value. There's another term here. In order for that to lie in the positive orthant. So again, we have to have more nutrient present in order to support both the phytoplankton and the zooplankton. And you can see coming into this expression, so we've sort of set this up because in our conservation law, we had the kernel of the distribution that the mean, this is the mean delay comes in here. So this expression works for any distribution, and then but we can see how the mean delay is kind of important in determining sort of how much nutrient we have. And then L, of course, is the size of our spatial size. So those two kind of parameters of the system come in. Okay. So if we have no delay of diffusion, and this is sort of standard results, right? You can just do standard stability analysis, and you can do some other work because we can reduce it to 2 dimensions, and there's lots we can say. If we're less than this first threshold, then our nutrient-only equilibrium point is globally asymptotically stable. If we're between the 2 thresholds, then the equilibrium point with nutrient and phytoplankton is globally asymptotically stable, and the EN is unstable. And then once we go past the second threshold, the EN, so nutrient only, and the nutrient phytoplankton are both unstable, but the stability of the third one depends on the form of the uptake function. Okay, that's one where I said we could do sort of type 2 or 3. And basically, if we do type 2, there's another threshold where if we're below that threshold, it's asymptotically stable. But if we go above that threshold, essentially there's a Hopf bifurcation and it loses stability, and we can get oscillations of the three variables. In the type 3 is actually quite a little bit tricky because it depends on what your equilibrium value of the phytoplankton is, which depends on these other parameters in the model, death rate and uptake coefficient. So if there's a certain criterion, if you satisfy this, then once you create the NPZ equilibrium, once it becomes into the, it becomes possible because there's enough nutrient, it's just always asymptotically stable and nothing else happens. But if our parameters are slightly different, then essentially it looks like type 2. So it's kind of the type 3, sometimes people just think, oh, it's sort of more stable and we don't get the Hopf bifurcation, but it really depends in a delicate way on the parameters in your system, what can happen. Okay, and then you could have like this is like a nice bifurcation diagram for the ODE system. Essentially you have, as you increase the value of nutrient, you have transcritical bifurcations where we go from, here, we have the nutrient only equilibrium first, and then we get the one the phytoplankton one, and then eventually we get the zooplankton one. And there's kind of interesting how the other ones vary. And then if you have the type 3 for large enough N3, we can get these Hopf bifurcations where we get oscillations of the 3 variables. Okay, so what happens if we put in the delay in the diffusion? So we had a few things. Most of these are sort of, yeah, we tried to make some, independent, like delay independent, diffusion independent type results. So the first one says, if we look at these, so like the nutrient only or the nutrient phytoplankton equilibrium. So the first one says, this says for any values of the diffusion, then the nutrient only equilibrium point is asymptotically stable or unstable. It only depends on that threshold value. So essentially the diffusion and the delay don't affect the stability of that nutrient only equilibrium point. If we look at the equilibrium point with nutrient and phytoplankton, it's a little bit interesting. You have essentially a boundary. You can guarantee it's stable between sort of 2 points. And it's not distribution independent because you have tau in here. So it depends on the mean distribution, but nothing else. So you can sort of say in terms of the mean of the distribution of the delays, when is that equilibrium point stable, but no dependence on the diffusion here. And this one becomes unstable for NET, once the NT gets big enough, then it loses stability and the distribution and the diffusion doesn't affect that. And I think I have a little picture, right? So I had to kind of quantify this. This is delay here. This is amount of nutrient. So under this line, we only have the nutrient only equilibrium point. When we pass into this region, we get the nutrient phytoplankton equilibrium point. The stability is kind of interesting how it depends on the delay. Basically up here, it's stable for any delay, but when you're down here, it can depend, well, up here for any delay, and down here it can depend on the delay in some way or the distribution in some way. And then once we cross this line, that's crossing the threshold NT2, and then it just loses stability, regardless of whatever distribution or whatever diffusion you have, and then it goes into the other equilibrium point, which we have a second, which is kind of the more interesting one, and that's when we have coexistence, the nutrient phytoplankton and the zooplankton. And basically, it says we have a sort of less strong result. It just says if the diffusion constants are all the same, then the diffusion doesn't affect the stability. And so, but we can say a little bit about how the different distributions affect the stability. So this is the same nutrient delay picture as before, but now I'm zoomed up into the region above where this equilibrium point exists. So it becomes positive in this region. And what I plotted here is some difference. So the dashed line is if we take a discrete delay, so it's stable below here, we essentially have a Hopf bifurcation if we go above there. And if you take a gamma distribution with different p values, and then we've got the mean delay plotted here, you can see how as the p gets bigger, so that's making the gamma distribution skinnier, it's sort of staying closer and closer to the plot, the curve of, where you lose stability for the discrete delay, which makes sense, right? As the gamma is getting skinnier, it's getting more and more like a discrete delay. What's interesting is, remember we had a Hopf bifurcation in just nutrients. So if we know delay, we could have a Hopf bifurcation in the case of, this is with the type 2. And you can see how these curves come out of that Hopf bifurcation. So there's places where adding the delay actually stabilizes, right? So we have a lot of nutrient here, and so up here we would have oscillations, but if we add some delay, we actually stabilize those oscillations. And in some ways, because then somehow we're taking some nutrient out of the system and now it's being recycled. So that's kind of an interesting result. Yes, and this is just, looking in a little more finely at the discrete delay. So in the last one, I showed that curve with the discrete delay, and that was for the type 2. age for the phytoplankton uptake of the zooplankton uplink to the phytoplankton. Oops, I'll take it back. And then you can see what happens in the type 3, right? So we had no hop bifurcation possible without delay, but now we can. So this is a curve of hop bifurcation that can occur. So if we add in the delay, then we can lose stability of the equilibrium point and get oscillations. But look at the scale here, it's quite different. So you need a much larger delay to actually see those kind of oscillations. Now, the physical values we found in the literature were quite broad, so it's hard to narrow. You have to be very specific, I guess, about what zooplankton and phytoplankton you're looking at and what your particular system is to. So this is still within the range, and this is also, we sort of looked at ranges of NT, but you have to be more specific about your particular system, I think, if you want to go from there. Okay, so then what happens if we start putting in the diffusion? So the basic result was, and then just focusing again on this coexistence equilibrium point, the basic result was if we had all the diffusion constants the same, then you couldn't get basically diffusion induced instability. The diffusion was sort of stabilizing if all the constants were the same. But something I won't talk about, what my other student E1 looked at was, so essentially if you're stable, you have a small enough nutrient that it's stable, then the diffusion can't make it worse. You can't destabilize it. But if you have enough nutrient present that you're unstable, then it turns out that you can get the diffusion actually causing a Hopf bifurcation. A Hopf bifurcation of an unstable equilibrium point, but in our simulations, we could see that it actually still produced interesting spatial temporal dynamics. So that's what's in the 2021 paper, which I'm not going to show today, but I wanted to mention that. But here we looked at the sort of preliminary results that Matt looked at, and we haven't really gotten back to, was what if we start thinking about different diffusion constants, right? So what can we see? And so we decided to sort of make a choice. So D1 is the diffusion for the nutrient. So we started to think, well, maybe that should be the biggest one. I mean, that was just a sort of, and then we scaled the other ones with that, and so D2 and D3 are for the phytoplankton and the zooplankton, and we took those to be quite small so that the sort of the nutrient can kind of float around and the other stuff is maybe not so floating around as much. And then the D4, which was the stuff that's being recycled, we took the two extremes, one that it's the same as the nutrient, so it's being recycled as sort of like nutrient, and the other that it was more the same as the other guys. So that was sort of the two cases we looked at. This is all with the type 2, and this was with a discrete delay. And so here was the Hopf bifurcation curve with no diffusion. And then here's, we did this because now we have just one diffusion constant to play with. And as we vary the alpha here, yes, let me just. Yeah, we took a particular D1, we scaled these. As we varied the alpha, you can see sort of the effects. So we could again see the Hopf bifurcation, and now it's sort of modulated by the diffusion. So when we had sort of a high diffusion constant, we don't need quite as much nutrient to cause the Hopf bifurcation. And then this, as the alpha gets bigger, it's kind of moving down. And then this was the other case where we took the D4 to be D1, and we see sort of the same thing. So, I mean, the basic effect here was introducing this different diffusion constant that we could, we wouldn't need quite as much nutrient in the system to start to see these oscillations. And the final thing I want to show is just some simulations to kind of, and again, this is sort of preliminary work. We haven't really gotten back to this different delay case. What we're doing here is, yeah, basically taking a particular value of NT. So I think, let me just, oops, go the wrong way. So we're taking a value of NT somewhere in here, and then we're kind of going through this curve to kind of see what's happening. So we kind of expect, yeah, to see what's going on there. And then, yeah, because we're increasing the delay. So we have, I haven't shown you this is nutrient, phytoplankton, zooplankton, this is space, this is time, and then we've taken 3 different delay values. And so we can sort of see here with the smaller delay, so the nutrient is kind of more homogeneous because it's got a bigger diffusion constant, and we see sort of a spatially homogeneous equilibrium, sort of inhomogeneous equilibrium solution coming out here. But as we increase the delay, it seems to sort of homogenize thing, and then we end up with spatially homogeneous oscillations, right? So it's kind of interesting playoff between the diffusion and the delay there. And this is all discrete delay for this case. And then this was sort of the other extreme where we took the D4, which is the recycling stuff, to have the same diffusion constant as the nutrient. And then we compared the type 2 and the type 3. And so as we might expect, the type 3, not much, that's the one where it's sort of hard, and the delay was fairly small. That's the one where it's fairly hard to get any instability with the delay. And essentially, we start off with kind of an inhomogeneous initial condition, but eventually it just spreads out and everything's homogeneous. But with the type 2, we actually got some quite interesting results here. So we see, again, over time, this kind of varying, this is the nutrient, sort of varying, it's sort of homogeneous, but varying in time, and then kind of these interesting little patches coming out with the phytoplankton and zooplankton. And again, this is sort of preliminary. Need to get back to that, need another student. I think that's basically all I want to say. So let me just give you my conclusions. So what we found was the stability of, what we call the extinction equilibrium, that's the one only with nutrient, and the spatially homogeneous phytoplankton only were basically unaffected by the diffusion, and then we could show, actually not really unaffected by the delay, but we could show how the mean delay of the distribution affected that. And if the diffusion constants of all the species were the same, then essentially the diffusion had it didn't affect the stability of that coexistence equilibrium. The delay can stabilize the diffusion-induced instability, and it can also stabilize just this even without diffusion. And the type of functional response is really important in determining the behavior of the model. So like with the type 2, we could have oscillations even without delay and without diffusion. With the type 3, we could get delay-induced oscillations, but we need a much larger delay in that recycling time. And with type 3, the diffusion really seemed to have not very much effect on the stability of this coexistence equilibrium, at least for the small delays, whereas type 2, we could see quite different things and quite interesting behavior coming out of that diffusion. And so let me just finish by thanking my collaborators, Matt and Francis, NSERC. Matt was also sponsored by Ontario Graduate Scholarship Program. And again, I want to mention Yiwen Tao, who was sponsored by the China Scholarship Program. I don't know the right term, but anyway, she came and visited us for a year. Most of it she spent locked down in COVID, so we did everything online, but she was an awesome student. And so that's kind of the follow-up work. So thank you very much.